All right, picking up where we left off, we said that there's a certain amount of light that could be considered the visible spectrum being produced by things like our sun. And then there's a certain amount of light on that visible spectrum that's visible to humans. And then there's a certain amount of light inside of that that can be reproduced by electronic equipment so that it can be shown on monitors or screens. Now, we were just saying that in order to talk about it, we need to have some math behind it. And that part of that math is defining what white light is. And in this case, we'll be using something called the D65 in order to represent it. Another pretty common one is the D15, I believe they say. We're not going to get into the details on that or even talk about the math. We really just want to talk about how this diagram is readable by us as human beings. So let's go back to our iPhones. Now, I mentioned that Hewlett-Packard and Microsoft produced something called sRGB, or standard red, green, blue, to be a sort of roadmap for how a monitor should be able to reproduce light. Now, that's the one we tend to set things to, sort of. There's a little bit more and we're almost there. Bear with me for just a minute. Now, different equipment can produce different amounts of light. And so now we're really starting to get into what these mean. They hopefully is making more sense. Somewhere out on this grid is all of the light that's visible by, that could be considered visible light that organisms would be able to see. However, some of them would be insects that can see ultraviolet light. Some of them would be maybe snakes or mice, which should be able to see into the infrared spectrum. I think mosquitoes also can see into the infrared spectrum, things like that. But humans can only see a subset of all of that light. And remember, this is supposed to be 3 coordinates, so they drew the third one as this weird bendy line going across. And there we have all of the color that a human on average would be able to see. Now, keep in mind, some humans can see more or less. There are certain eye surgeries that replace the lens, and then you can see into the ultraviolet and all that. But this is just sort of a standard human perception range that was determined by the International Commission on Illumination. They just kind of worked out several measurements, and then they got this average. So we've got that. Now we've determined a way to mathematically state what white light is, and so that it's actually, hopefully white and not orange or blue or any of those things. And we'll label that in the center. Now that we've got all that, we need to figure out how much of the blue light it can reproduce, how much of the red light, and how much of the green light. And those will essentially be your short wave lengths, your medium wavelengths, and your long wavelengths. And why do they call them that? Well, if you start doing measurements at, I believe it's the nanometer level, you'll see that the blue ones are considerably shorter than the red ones. Now, that's minuscule. That's incredibly tiny measurements. That's not something you could actually draw with the pencil, because your pencil could never be sharp enough to draw the nanometer line. It's just impossible. But our cones are capable of picking those up, or at least when there are a lot of them firing off in a pattern, we can pick them up. Anyway, so if we start mapping these out, we can see that compared to the sRGB, which is a standard monitor from like 1996, Microsoft and Hewlett-Packard were figuring out the old iPhone 4 could produce actually more blues, but fewer greens. So there are colors that if you were to use in an image, those colors would not show up on the iPhone 4 the same way that it would on an iPhone 5 or an sRGB monitor. And so at that point, you'd probably see something in this line. So those would be compressed down. You'd have more yellows that you could show off than you could actually see on these old iPhones. Now, when I was getting into computer graphics, Macintosh monitors were produced differently than other monitors, and they were known for having better and more vivid blues than most sRGB monitors. These days, I believe Samsung produces the bulk of the Macintosh monitors, and so they have about the same color range as anything else. That said, if you were to produce something like, say, an Apple Watch, you may not have the exact same colors. So at what point, how do you get access to which colors are which ones are inside of a range and which ones are outside of a range? Well, you need a color profile. Now we're finally getting to it. So if you had a color profile, it would be a way for the computer to know what colors that you're reproducing with your 256 levels of illumination on red, green, and blue, what colors will be reproduced accurately on one set of screens and inaccurately on another. So you could get warnings and such, and you could actually see those colors reproduced or not. Now, this will get us into color gamut, so let's talk about that for just a moment. So color gamut in color reproduction, including computer graphics and photography, the gamut or color gamut is a certain complete subset of colors. The most common usage refers to subset of colors which can be accurately represented in a given circumstance, such as within a given color space or by a certain output device. All right, what? Well, the complete subset of color, this is just what we've been talking about the whole time. Take a look at this triangle. Take a look at this horseshoe shape. Take a look at this grid. It's what we've been talking about. All it's saying is that it's the range of color. That's all. Now, this gets a little more interesting. Pop this open. We are using sRGB, but another default is Adobe RGB. Now, Adobe RGB is a set of colors that actually encompasses the sRGB, but it goes past that. And so the Adobe RGB has within its range some more greens available to it than you'd see inside of the sRGB, some more reds and a few more blues. So you have a better gamut, essentially. You can reproduce it. Now, there is another question, can your monitor support that? And you'll have to check your monitor's manual in order to know for sure whether or not it can. But if you start getting things like high definition TVs and ultra high definition TVs, let me see if I can pull one of those up. Here we go. You can see that things like the ultra high definition televisions actually have a humongous range of colors available to them. So you'd be able to load in an Adobe RGB profile onto an ultra high definition TV and have no worries about reproducing all those colors. You're set. You can see them, right? Well, maybe. So we've stored the profile, right? We've been able to stash these away, and I demonstrated how to do that under edits and then assign profile, and you can see that this may change the appearance of layers. It's fine. You can assign your profile and you can store it with your image, right? Not a problem. But if your television can't display that, it may end up getting some weird colors. But let's say that your television can display that, or your monitor can display that. You have a monitor capable of far larger gamut of colors than the one that's stored inside the file that you're saving and moving from one computer to another. That should do it, right? You load in this profile and then you can see it. It will go, oh, let me map the D65 white light point. Let me map this 255 color here and this 255 color there and this one there, and voila, we'll be able to re-represent these and everything fit, and you're completely safe. Not quite. There's one more step to all of this. So you've got the profile stored and stashed and everything's good, but your monitor still has to be calibrated in order for things to work. So let's say that you get your monitor fresh out of the box, you plug it in, and you notice that things don't look quite bright enough. So you start to do things to attempt to adjust that, and you go into the settings and you start changing the brightness and you start changing the contrast and all that. Well, the computer might need to know what's going on too, so you can actually set it up so that most operating systems are in control of those settings. It can tell your HD TV or whatever you have plugged into your computer, even if it's an old CRT screen, you know, those big bulky ones that make the humming noise, like any of those guys. The operating system is generally now able to control what's going on, but it needs an outside viewer to tell it what's happening. So let's say that you came in and you had what it thinks is a gray square and what it thinks is maybe a black square and what it thinks is a white square. And so it would show you this and it would say, hey, just real quick, if you could look at this, since you're an outside viewer, does this look as white as possible? Does this look as black as possible? And does this gray look like it's in between? And if you say no, it will come up with some little levers and adjustments, and you'll start moving those around until, you know, it shows as actually being white and black. Now, you're able to do that because you're an outside observer. But there's more to it than that. Remember how we said that certain lights are orange? Well, some are blue and some are all different colors altogether, which means the room you're in, depending on the lighting that you have, white, black, gray, all those may look slightly different. You may be looking at a white square and it may actually be white, but the color cast of the room makes it look blue. And so you have to adjust for that so that you can see it. But then, you know, it's late at night, you have certain lights on. The next day, you have more natural light coming in. All of a sudden, it's wrong again. And you need to reset everything. So they've started to do things like include sensors inside of monitors that can try to detect the level of light and be its own outside observer so that it can switch between different settings on your screen, so that when it loads up its color profile, it maps white to white and black to black and gray to gray, and everything looks correct. It maps blue to blue and red to red and green to green. Now, this gets interesting because you can go even further. Let me bring up a little device for you real fast. There we go. Now, I'm not endorsing this. This is just the first example that came up. These little devices are pretty funky. They essentially have a bunch of little cameras on one side, and then they have a sensor, another one on this side, and then you just stick it on your monitor. Thusly, let's see if I can get this image a little bit bigger, on your monitor, and it will plug into your computer with USB. It has software, and it will recalibrate your monitor for you, and it becomes the outside observer. And it checks the ambient light in the room, and it checks what is supposedly red and supposedly green and supposedly blue and white and gray and black and all that on your screen. And it goes, I'm not actually picking that up. The light meters that are inside of this are saying that those are not correct. Let's go ahead and raise it or lower it or what have you until it is correct. So these things will actually calibrate it for you. So they can be very, very useful if you're doing a lot of work as a cog in the machine, so to speak. If you're one studio amongst many studios, and film and television would be a good example of this, you need to make sure that the adjustments and the color corrections you're making are the same kinds of adjustments for everyone. In other words, if you're working in an orange room, you don't want to be correcting as though your white light is orange, and you'll make everything wrong and weird. And then when you send it off to the next studio, they'll complain. You need to make sure that you're constantly calibrated. Now, a few years back, you could actually, you'd see interns and things running around, and even professionals who all they do is run around throughout the day and recalibrate monitors to ensure that all of your monitors are, correct. That white is white and black is black and gray is gray, and all the blues are blue and all that, so that when you load in a color profile, you actually see and what that color profile is correctly. So when the next studio gets it, they'll be able to see the same thing you're seeing. Well, now they have even more tools. You've got all these cameras you can slam on it, and they can readjust it throughout the day too. Now, why would you have to do it throughout the day? Well, with natural lighting, as the sun moves throughout the sky and as you get more or fewer clouds, the colors are going to change, and you're going to have more light or less light, so you need to adjust everything again. So that's the other half of the equation, the actual physical monitor. Now, that said, I'm going to dig out and post some videos on the class website for calibrating your monitors. Now, monitor calibration differs depending on your operating system and your hardware, so take these with a grain of salt, and these change frequently, so even between the time that I post it and you see it, there may have been an update to Windows 10 or to your Macintosh operating system. I think Catalina's coming out soon. In which case they may be wrong. So take them with a grain of salt. It's just an idea of how it might work, not necessarily the nitty gritty. You're going to have to check your manual to do it and experiment. That said, be cautious. I've had students get really into this, and for the first few assignments that they start turning in, their colors are completely wrong because they'll miscalibrate their monitors. So even though they have the same color profile, we're not looking at the same thing because their monitors were blue or something. And so they compensated for it when they were recoloring it. Then when we showed it on screen, they could clearly see that it wasn't right. So do watch out for that. If you are calibrating, do it a couple of times. See if you can check it maybe on your phone or on a friend's computer, or if you happen to have access to two different computers, check the image on two different computers. Make sure that things are actually going once you've calibrated it. Again, these videos are to demonstrate ways to calibrate, but they may not be precisely the same calibration methods that you'll use from monitor to monitor. All right, so that said, that should just about cover it. So let me say again very briefly what the heck is going on now that we've rambled our way through this whole thing. Inside of the software and inside of the file, you can have different color profiles assigned to it. Those color profiles are defined by mathematicians and engineers as a way of measuring out gamut, that is a range of color, so that you can predict from one system to another how it will be displayed. You include this, and if the system that you move it to is calibrated correctly, one blue on one system will be the same blue on the other. The calibration of the actual hardware has to be done by a human or by an external device, some outside observer who can take into account things like the room's ambient light and the color cast of the room, and then adjust accordingly. If everything is calibrated correctly, that color profile should allow you to see the same colors regardless of which screen you go to. All that was measured out years ago, and in fact, how long ago? Well, at one point, 1931, but guess when it was updated again? If we were to create a new document, notice that it's IEC, in other words, the International Commission on Illumination. Notice that it's most likely, I believe, their sixth meeting, if I'm reading that correctly. They met that time in 1966, and this is version 2.1. That's what all of that's referring to. sRGB is just the standard red, green, blue that Hewlett-Packard and Microsoft figured out. Now, if you want a larger range, you'll have things like Adobe RGB 1998. I'm just going to use the sRGB because it doesn't matter how old your system is. It's the smallest range and it will work fine for your assignments. But if you're working at home for something else, not these assignments, probably Adobe 1998 would be the way you'd want to go. Quick warning on that, they actually stole a lot of their they stole a lot of their schematics when they did this, and there were some copy errors, I believe, in the blue range, but it should be fine by now. They worked all that out years ago. Just a fun fact of theft going between companies. If you're doing things for television, find out what they want, and you can set that up accordingly. So for use outside of the class, Adobe RGB 1998 will give you a wider color range, and these days on monitors, it's a safe bet that they'll be able to reproduce it. For this class, go ahead and stick with sRGB. It's a small color range, as we've seen through all these little diagrams that I keep bringing up, but it's also a safe range to work in. We know that it will show up pretty much fine on anything, so we'll stick with that. All right, so you apply those color profiles. And then once they're stashed away inside of here, the colors that you see will hopefully be the same as the colors that I see. That's about it. That's about 40 minutes to talk about all of that. Hopefully it wasn't too rambling. And if you have any questions, let me know. I'll be happy to clarify anything. I'll just record another video or respond to emails, however you prefer, and we'll pop that right out. That said, let's get into how color is handled inside of Photoshop. And from there, we can get into recoloring an image. Catch you in the next video.